We will now look at maximizing and minimizing our economic functions. Recall that the economic functions that we have worked with are cost, revenue, and profit. So which of these do we want to maximize and which do we want to minimize? There are obvious business advantages to maximizing revenue, how much money our company brings in, and maximizing profit, how much money our company gets to keep. So let's look at an example. Suppose that we sell toy trucks at a store for P dollars. The quantity that we sell in a week Q depends on the price and is given by the demand function Q equals D of P equals 60 minus 3P. Recall that with our demand function, as the price goes up, less people want to buy it, so the demand goes down. So what should we charge to maximize our revenue? Since we are trying to maximize our revenue function, we first must find our revenue function. Recall that revenue, R, is price times quantity, which in this case is P times 60 minus 3P, since the quantity is given by 60 minus 3P. Multiplying this out, we get negative 3P squared plus 60P. And now to maximize this function, we start by computing when R prime equals 0. Computing the derivative of negative 3P squared plus 60P, we get that R prime equals negative 6P plus 60. Since we want to find when R prime is 0, we need to solve 0 equals negative 6P plus 60. Doing this, we get P equals 10. Remember that so far we have only found that P equals 10 is a critical point, but is this critical point a maximum? To check, let's use the second derivative test. Computing the second derivative of R, we need to take the derivative of R prime, which is negative 6P plus 60. Its derivative is negative 6. So we need to know, is R double prime at 10 positive or negative? We see here that R double prime is always negative. So in particular, R double prime at 10 equals negative 6, which is negative. So by the second derivative test, P equals 10 is a max. So to maximize our revenue, we should charge $10. But the question that remains is, what is our maximum revenue? To find this, we need to evaluate our revenue function at P equals 10 to get that R of 10 equals negative 3 times 10 squared plus 60 times 10, which is 300. So our maximum revenue on toy trucks is $300. But is maximizing revenue our goal? Not always. We usually want to look at maximizing profit. So what is the maximum profit? To do this, we need to know our profit function. And to know our profit function, we need to know our cost function. To know this, we need more information than we were originally given. So suppose that our store buys the toy trucks from the manufacturer for $6 each. Then our cost function is 6 times Q, which in this case is 6 times 60 minus 3P, which is 360 minus 18P. Now that we know our cost function and our revenue function, we can find our profit function, because profit is revenue minus cost. In this case, we get that profit is negative 3P squared plus 60P minus 360 minus 18P, which comes to negative 3P squared plus 78P minus 360. Now that we know our profit function, we can maximize it by finding when its derivative is 0. Computing its derivative, we get negative 6p plus 78. And solving this equation for p, we get that p equals 13. So to maximize profit, we should charge $13. And what is the maximum profit we can have? To find this, we need to evaluate our profit function at price p equals $13. Doing this, we find that profit is negative 3 times 13 squared plus 78 times 13 minus 360, which is 147. So the maximum profit our store can make selling toy trucks is $147. It's worth pointing out that here, and in general, the price to maximize profit is typically different than the price to maximize revenue. So far, we looked at maximizing revenue and profit. But what about cost? Does it make sense to maximize cost? No, of course not. Does it make sense to minimize cost? Also no, which might be surprising. The reason is, to minimize cost, simply don't produce anything. My unicorn pet store has no costs at all. It also has no revenue because it doesn't exist. So it doesn't make sense simply to minimize cost. So what do we want to do? Instead, we want to minimize average cost. That is, we want the lowest cost per unit made. So let's now understand how to minimize average cost. If our cost function is given by C of Q, then the average cost, A of Q, is C of Q divided by Q, the number of items we make. Suppose that the cost to produce Q widgets is given by C of Q equals 0.001 Q cubed minus 1.2 Q squared plus 3Q. What is the minimum average cost? To find this, we first must find average cost, which is A of Q equals C of Q divided by Q. In this case, 0.001 Q cubed minus 1.2 Q squared plus 3Q all over Q, which comes to 0.001 Q squared minus 1.2 Q plus 3. So to minimize it, we need to find when A prime of Q equals 0. Computing A prime of Q, we get 0.002 Q minus 1.2. Solving for Q, we find Q must be 600. So to minimize our average cost, or cost per widget, we should produce 600. So far, we have simply found that Q equals 600 is a critical point, but is it a minimum? To do this, let's use the second derivative test. A double prime of Q equals 0.002, which is always positive for any value of Q, including 600. So, by the second derivative test, at Q equals 600, we have a minimum. Now that we know the minimum average cost happens when we produce 600 widgets, we need to find what the minimum average cost is. To do this, we simply evaluate our function A at 600, which is 0.001 times 600 squared minus 1.2 times 600 plus 3, which comes to 3. So that means that the lowest we can produce widgets for is $3 per widget.